Okay, so we have made it to the final part of this course, where we're going to pull together a whole lot of stuff that we've talked about throughout the semester. So we're going to be using exponential functions, which we started off with, talking about differential equations, and bringing it all together with the matrix stuff that we've been doing. So I hope you'll get a feel for why I structured the course the way I did, so that we could finally get to this point. Okay, so if you cast your mind back to tutorial 4, we were looking at a situation where we had two tanks. We had water flowing into tank A, and inside tank A it started off with some water and some salt. Then the salt and water mixture, which is called brine, was being transported into tank B, and where it was also being mixed, and then out of tank B at a certain rate. And we're assuming at all points that the mixture is well mixed, so we don't have salt down at the bottom. So this is a kind of a simple situation, but it is something that might crop up in a more complicated version if you have multiple chemical reactions and things moving from one system to another, and you want to figure out how much of a particular reactant there is in each system at a given time. So we worked out in tutorial 4 that if we looked and we let x of t be the amount of salt in tank A at a given time t, and we know that that's going to change because it starts out with a certain amount, but then the brine mixture is leaving tank A and fresh water is coming into tank A, so it must be changing. And similarly, tank B starts out with fresh water, but then brine from tank A comes into it, so its salt amount is also changing. So we've got y of t is the amount of salt in tank B. And we were given some initial conditions, which said that initially there's 100 kilograms of salt in tank A, maybe 100 grams, that might be more reasonable, and none in tank B, and then it changes. And if you work through the tutorial, we came up with these two differential equations, which together model the amount of salt or the rate of change of the amount of salt in the two tanks over time. So this equation tells us what's going on in tank A, and this tells us what's going on in tank B. So this is the kind of situation that we'd like to solve. We didn't actually solve it in the tutorial. I gave you two solutions, and and hopefully you showed that they were solutions. But the question is how would we find those solutions? Now, we're not going to get quite there in this course, but I'm going to get you most of the way there, and then you can hopefully figure things out if you ever need to in your future life doing whatever you're doing. Okay, so as usual, going from our example, this is a specific example of a general case of what is called a system of linear differential equations with constant coefficients. Okay, so there's a lot of words going on there. We know that these are differential equations, so we don't have to worry about that. Why are these linear? Well, we've talked about linear functions already. These are functions where the variables only occur as themselves. There are no powers, there are no cross terms, so we have no xy terms, nothing like that. So the linear bit is where we just have x and y appearing just as x and y, and constant coefficients because we're assuming that the things that are multiplying our variables are just constants. And you can go further and have variables and have functions there, but we're just assuming that these are constants. Now, obviously, you could extend these, so you could have more variables, more equations, but for this course, we're just going to stick to this 2x2 situation. And you can get the hang of it. Going to more dimensions isn't really that big a deal. There are a few little wrinkles, but you get the basic picture. Okay, so now we bring in matrices. We're going to let our matrix A be this bunny over here, A, B, C, D, and we're going to write X, so this is a matrix, that's a bold face there, as the vector that consists of our x of t and y of t as two components. So this is a vector, but it's also a function because it's taking in a time component, and that will give you the two components at a particular time. Why would we want to do this crazy thing? Well, it's going to enable us to rewrite our system of differential equations as follows. So let me just add a bit more paper here. So what have we got? Well, I'm going to, firstly, just to keep things kind of neat and tidy, I'm going to write this as x prime and y prime. Those are just my dx by dt and my dy by dt, but it's just going to keep things easy. And I'm writing that as a matrix, in this case a vector. And then I can also write each side, the right side of each equation, like so. Now I haven't done anything particularly spectacular yet. I've just basically taken two equations and turned them into one equation with a vector on either side. But notice that I can actually undo some matrix multiplication that you maybe didn't notice had happened over there, and I can rewrite this as matrix ABCD times the vector xy. So you can check your matrix multiplication, and you'll see that if you do this multiplication, you end up with that over there. And now I can go one step further, just in terms of neatening up my work, and I'm going to write this equation as x bar prime. So I am now thinking of this vector here as this, the derivative of this bunny up here. It gets a bit frustrating because I'm using x with a bar on top to represent the vector, which has coordinates x and y. Sorry, but this is the kind of thing mathematicians do. I apologize for my species. Okay, so that's the left-hand side, and now over here I can write this as a times x. And now I have a beautiful matrix equation, not one that we've really seen before because we haven't seen derivatives, but nonetheless, it's an equation, and everything that we've learnt about matrices now applies here. Okay, so what can we do? Well, now we'd like to actually solve that matrix equation. So we've solved, if you recall, we've solved things that look like ax is equal to b, where this is some constant. Now we're doing something slightly different. We're solving ax is equal to the derivative of x. But this is really just differential equations. We know kind of how this goes. We also know quite a lot about how to solve things like this, and we're going to blend them together to get a solution. So the first thing you might think is, okay, well, what's the simplest solution I could think of? And since we're talking about differential equations, we can think about simple solutions which are constant, otherwise known as equilibrium solutions. So if you have a constant solution, then obviously your derivative must be zero, because if your x and your y are constants, they're not changing, the derivative is zero. So one thing that you could do is find this equilibrium solution, which we generally denote x naught, y naught, to mean specific constants, x and y, that are not changing. You just solve this equation over here, which is really this thing over here, except now your derivatives are equal to zero. And we're looking for specific values for x and y. And that is a straightforward system of linear equations that you know very well how to solve. So there you go. System of linear differential equations, first solution done. But of course, we would like to find some solutions which are not constant solutions. So solutions where our derivatives, our time derivatives of x and y are not zero. And in order to do that, we are going to do something cunning. We are going to use our eigenvalues and eigenvectors. So let's see. Now suppose that we could find some non-zero vector v naught such that our a times v naught was equal to lambda times v naught for some real number lambda. Now at this point you should be going, We know this. Okay, so basically what we're saying is, suppose we could find an eigenvalue and an eigenvector that satisfy our matrix A. Remember, our A is this A, B, C, D. How is that going to help us? Well, I claim that if we have that eigenvector and that eigenvalue, that this thing here is a solution to the system. So this thing here, if I write it out as vector in components, says e to the lambda t. So that's going to give me a time component times whatever the, I'm going to put vx and vy, so times by the x and y coordinate parts of the eigenvector. So I haven't proved this yet. All I'm saying is that if we have a system of linear differential equations like this, and we can find an eigenvalue and its corresponding eigenvector, then my claim is that if I construct this thing over here, that is going to be a solution to the system. Could it be? Well, let's check. So in order to be a solution to the system, so my claim is that this thing here, x of t, solves this equation. Well, to check that it solves it, let's just differentiate it. So I'm going to say, let's differentiate so that might look a little bit hairy. Let's differentiate it in this form over here. So I'm going to differentiate it term by term. So I'm going to get x prime of t. So that component is going to be the derivative of whatever this is. Now we know that our eigenvector is a constant, so that's not changing. So the only t component that I have here is in here. So I'm only really differentiating e to the lambda t. And we know that the derivative of e to the lambda t is just going to be lambda e to the lambda t, and then we've got to have this times the component, the x component of our eigenvector. And the same thing is going to happen for our y component. So we're going to have the derivative of y of t is equal to, same thing, except with the y component. But now if I pull out my lambda e to the lambda t, then I end up with this. But notice that this bit over here is just our original x of t. So this is in fact equal to lambda, oops, not x. Yes, actually lambda x of t. So what I've got here is that x prime of t, where I'm thinking of this as the vector. So we've just shown that this is true. Okay, so far so good. Now let's look at the next bit. I want to have a look at a times x of t, where I am considering this particular solution that we're proposing here. Well, in this case, it's going to be a times e to the lambda t times our eigenvector. And remember, this is really just, it's a scalar, so we can move it around in the multiplication wherever we like. So we could rewrite this as e to the lambda t a v naught, but our v naught is an eigenvector, so we know that A times our eigenvector is the same as the eigenvalue times the eigenvector. So this is going to be e to the lambda t times lambda v naught v, and then a little bit of rearranging and we get lambda e to the lambda t v naught, but we know that this is our original x, so this is equal to lambda x of t. So finally, putting it all together, we wanted to show that our solution solves this equation over here. Well, we've taken the left-hand side and shown that it equals this, and we've taken the right-hand side and we've shown that it equals the same thing. So we conclude that putting these two together, we've shown that our x of t equal to e to the lambda t times our eigenvector solves the equation that we were interested in, which was this thing. Okay, that was slightly rushed, but it follows the basic idea that you know from way back when, which is if you want to check that something is a solution, you show that the left and right hand sides of the equation that you get when you substitute it in are equal. And we just did that. Okay, so that's quite a big thing that we've just done, because we've just shown, going back here, that if we find the eigenvalues and eigenvectors for our 2x2 matrix, we can construct a solution based on those values. So let's... I was going to go and do an example, but I forgot about this slide. So you might be thinking, okay, can I just use any old eigenvalues? So we're not going to show it here, but in fact, you can show, and it's quite straightforward, and I will probably put it into the tutorial as a challenge question, that if you're a 2x2 and you have two distinct eigenvalues, so we'll deal with the not distinct case in a little bit, if you have two distinct real eigenvalues, then in fact you can construct what's called the most general solution by taking the solutions you get from each of those. Okay, so if you have distinct real eigenvalues lambda 1 and lambda 2 with their associated eigenvectors, then the general solution is given by some constant times the solution from the first eigenvalue and vector and some constant times the second. The constants shouldn't really surprise you. You know that when you're integrating, constants come up. We didn't show that this thing here was the only solution or the most general solution. We showed that it was a solution. So ultimately, what you need to know is you find the most general possible solution by combining the solutions of the two eigenvalues that you find. So let's see what that looks like. So we want to find the general solution to the following system, and it should look hauntingly familiar. We've actually done most of the work for it. So here we go. We found in the previous part that we had a first eigenvalue of 3, which had an associated eigenvector. And I'm going to use a different, what should I use? Let me use an S here. And we found also an eigenvector of -1. So I should have called this one my eigenvector 1, and this is my eigenvector 2. And this one was a 1, 1. So we actually only need one particular eigenvector for each eigenvalue. We don't need the whole family of them. So we pick a particular value of S, and I should actually probably give this one different. Let's call this R, just to be clear. So we pick a value of S and R, and that will give us two eigenvectors, not the whole family. So I'm just going to keep it really simple, and I'm going to call my, so let's call this V1 star, and I'm going to call this V1 is equal to 1, 1, and V2 is equal to minus 1, 1. We didn't have to pick those, so you could have picked different values for S. So you could have put S is equal to minus 62, and then your eigenvector would be 62, 62. The only values obviously you don't want to pick are 0, because then you lose all your information about your eigenvector. But any other values would do. You could have picked 3 for R, in which case you'd have had minus 3, 3. So you will notice that there are multiple possible options. There's no final single correct answer for your solution that we're going to get. But they are all multiples of each other, so it kind of makes some sense. Okay, so we want to put these all together into our solution. So our final solution is going to be, according to that up there, is going to be x of t is equal to some constant times e to the lambda 1, so that's 3t times v1 plus some constant b times e to the minus t times minus 1, 1. And this mightn't look kind of super convincing because you're not necessarily very familiar with looking at matrix equations, but if you write it out as x of t is equal to alpha e to the 3t plus beta e, so that should be a minus, sorry, minus beta e to the minus t, and y of t is equal to alpha e to the 3t plus beta e to the minus t. This might look more convincing as solutions to differential equations. I hope so. Okay, so that was quite a lot. There is more that you could do. So if we had a look at the system we started off with, if we found the eigenvalues for that, you'd find that there's actually only one eigenvector, one eigenvalue, minus 5/3. And when you have a situation like that, where you've got a repeated eigenvalue rather than two distinct ones, you need a slightly different method. It's pretty similar, and we could do it, but I feel like I've given you enough already. So my suggestion is, if you're interested, come and take my differential equations course next year. There's another system that we looked at, our predator-prey system, which started off our whole discussion of differential equations, and we haven't quite got there because that's nonlinear. So if you remember, in a predator-prey system, you have terms across terms, so you have an xy term. And again, we're quite close to being able to solve those, or at least approximate those, but not quite in this course. But you have all the tools. If you know about eigenvalues and eigenvectors, and you get familiar with your matrix multiplication and things like that, you're almost there. So hopefully with this course I've given you enough insight to go wherever you need to go with the maths in your chosen discipline from now on. But to get back to serious things, what do you need to know from this lecture? Please know how to write a system of linear differential equations as a matrix equation. That's not hard. And then if you get given a 2x2 matrix equation, differential equation, I will make sure that it has two distinct real eigenvalues. You need to know how to solve it. So essentially all you really need to know is that formula there and how to find your eigenvalues and your eigenvectors and put them in. All right, well, I hope you've had fun. I have. And we'll look at some examples in the tutorial to get you comfortable with everything we've done today. All right, bye.